Good evening, good afternoon, everyone. I forget which is afternoon or evening. Good afternoon, everyone, and we begin the last part, literally, of our journey in electrostatics. And if everything goes fine, we can pull this off in today's class as well. If not, probably it will move on to the next class. But we are on the last part of the edge of electrostatics, and that is good. And the last thing that we are going to do in electrostatics is electric dipole. Electric dipole, and I will try to combine two topics here together. What is electric dipole? Anyone knows what is an electric dipole? Please feel free to let me know what do you mean by an electric dipole. What is an electric dipole? Di means two, pole means two ends. Dipole, electric dipole. What is an electric dipole? Anyone? No one? Huh? I thought you were knowing what is an electric dipole. I thought that I thought that it has been already covered in your class. Yes or no? No, yes? Not covered? No. Covered? You don't remember. Is that so, or it is not covered? Okay, anyways, doesn't make any difference. You can write the heading electric dipole. What is an electric dipole? And this is the diagram that I want to show. Electric dipole is a system of two charges of same magnitude, but opposite in nature, opposite in sign, separated by a very small fixed distance. So there's fixed distance. You can think it of as a dumbbell. Have you seen a dumbbell? The student, the people do this dig dumbbell. So you can think of dipole as a dumbbell. There is a rod in between, and then they have two dumbbs, the bells, whatever you call them. So two charges, positive charge, negative charge, separated by a small distance, that is known as an electric dipole. That is known as an electric dipole. Do we understand this? Electric dipole. That is your electric dipole. So if you want to write the definition is very simple. It's a system of two charges equal and opposite in nature, separated by a small distance. This combination is known as electric dipole. Here the distance is shown very large, but it's actually not so large. This is just an exaggerated view of the dipole. I hope we understand this. Yes or no? No or yes? Okay. Now every dipole has got these two lines, and you can see these two lines. One is the pink line, and the pink line goes like this actually. The pink line has a direction, and then there is this green line which goes like this. It does not have a direction actually. This green line is known as the equatorial line or the equatorial axis, and this pink line is known as the dipole line or the dipole axis. They have their definitions as well. And what are the definition of these two? They are simple things, not very complicated. I hope you know them. Anyone knows what is the definition of a dipole axis? Well, it is the same as it is seen. So dipole axis is the line joining the negative charge to the positive charge. It is a line joining negative charge to the positive charge. So right now it is here like this, negative to positive. Why? I mean, whenever a line joins negative charge to the positive charge, it is also joining positive charge to the negative charge. Why it is said that it is negative charge to the positive charge? Because the dipole axis has a direction. This dipole axis has a direction, and remember the direction of this dipole axis is from negative charge to the positive charge, and this is what you need to remember. But that thing is not valid for the equatorial axis, because equatorial axis does not have any direction. So it is a perpendicular bisector, and it is known as the equatorial or transverse axis. Dipole axis sometimes is also known as the longitudinal axis. Small things, small terms. I hope everyone understands them. Yes or no? Then comes the next term, which we can also see. The next comes the next term, which is known as the length of the dipole or dipole length. You can see this dipole length in the diagram in this blue 2L. The distance between the two charges is known as the dipole length. You can call it as capital L. In this case, capital L is 2L. That is known as the dipole length. The distance between the two poles is known as the dipole length. Have you noted it down, beta? Shall we move ahead? Now, every dipole has two charges, one positive, one negative, equal. Every dipole has got a dipole axis, which is from negative charge to the positive charge. Every dipole has got a dipole length, which is the distance between the two poles. Now, whenever in general language we talk about a charge, we talk about what is the magnitude of a charge. Magnitude of a charge tells us what is the charge going to do, what is the effect this charge is going to have on other charges, or what type of electric field this charge is going to create. Whenever we talk about dipole, now what do we talk about? When you think about dipole, we don't think about what is the charge of the dipole, because charge of a dipole is actually zero, because one is positive, other is negative. So whenever we talk about dipole, every dipole is characterized or known by its dipole moment. See, this phone is known as an iPhone. I don't have the other one. That phone was known as Samsung. So everything is characterized by a name or something that tells us what is that going to do. Every dipole is characterized by a vector which is known as the dipole moment. And that is the most important thing that you must remember about dipole. Whenever we talk about dipole, we don't talk about the charge of the dipole. We don't talk about the dipole length of the dipole. We talk about this dipole moment of the dipole. What is dipole moment of a dipole? It is a quantity which gives information about the strength of the dipole. How strong that dipole is given by this dipole moment. The important thing, it is a vector quantity, and it is directed from negative charge to the positive charge. So it is along the dipole axis. The direction of dipole moment is along the dipole axis. It is denoted by P vector and is defined as the magnitude of either of the charge. We take normally the positive charge, and the dipole length, or I can write it as dipole axis. So I will write it, the dipole moment P, as Q multiplied by 2L vector, where this L is treated as a vector. This L is actually your this 2L is actually your dipole axis. So we will write it in this way. Do we understand what I'm saying? Are we getting this?
Yes, sir.
So if this is your dipole, positive charge, negative charge, your dipole moment, which is vector P, is going from negative charge to the positive charge. And if the length of the dipole is d, you can write it as q into d vector. Do we understand this? What all things you must remember about this dipole moment? Let us put them down point wise. What is the first point that you remember? Dipole moment P vector is a vector directed from negative to the positive charge. The value of this dipole moment is q multiplied by 2L vector. Q is the charge. The SI unit is coulomb meter. Coulomb is charge, length is meter. The dimension becomes LTA. Looks like quite L stand for length, T for time, A for ampere. LTA. Do we understand this? Yes or no?
Yes, sir.
Okay, great. Then there is a small question that is coming. Everyone has noted everything down? Shall we move on to the next question?
Yes, sir.
Boys?
Sir, 1 minute, sir.
Okay. I'll give you 1 minute. Don't worry. Let me know once you're done, bacha, so that I can move forward in life. Finished? Okay. Then this is a question coming for you. I hope you can read this question, tell me the answer, and then we can move ahead in life. A system has two charges. One charge is 2.5 into 10 to the power minus 7, and the other one is minus 2.5 into 10 to the power minus 7, located at point 0, 0, minus 0.15 meter, 0, 0, plus 1.5 meter. What is the total charge and the dipole moment of the system? You have 2 minutes to give me the answer. Do it aram se. Just apply the formula, get the answer, and you can stay happy. Yes, bacha, do we have any answers for this one? So, what is the total charge? Total charge, as Abhiram says, is 0, no problems. And then you can find the dipole moment. You can multiply charge 1.5 into 10 raised to the power minus 7, multiply it by the distance between the two. And I think the distance will be 0.3 meters. You multiply this and you get your answer for this one. I think the answer that you are going to get will be 7.5 into 10 raised to the power minus 8 coulomb meters. That is the dipole moment, and it is directed from negative charge to the positive charge. Negative charge is placed at point B, so it is directed from B to A. Everyone got this answer? Yes or no? No, yes. No one got this answer? What is such a difficult question? I thought it was simple. Anyways, I'll give you 2 minutes to note it down. Tell me if anything is troubling you here in this question. Anything that you did not understand, beta, please let me know. Everyone understands what we have done?
Sir.
Okay. So let me know once you have written it so I can move ahead. Was there any doubt, any confusion in this? Okay. Then we move to the next heading. Now, since this dipole consists of two charges, positive charge and a negative charge, this will also create an electric field. How do you find the electric field? So we will do it in two cases. Case number one, and you will have to remember the formulas that we are getting, and you will get a question based on these formulae. Case number one, on the axis of dipole, what is the electric field and what is the potential on the axis of dipole? Now, what do you mean by the axis of the dipole? What do you mean by the axis of the dipole? What do you mean by the axis? What has happened here? Okay. What do you mean by the axis of the dipole? So the line joining negative and the positive charge. Yes, Abhiram, that is correct. So this is what you mean by the axis of the dipole. Here I have taken the dipole as minus q and plus q, and the dipole length is 2L. Why we have taken 2L? Because from the center, both the distance become L and L. And normally what is given to you is a point is given. This is the point P where we are finding out the electric field. The distance of the point P is given from the center of the dipole. Therefore, we have taken the electric field. Therefore, we have taken the length of the dipole as 2L. Now, this positive charge will create electric field. This positive charge will create electric field in this direction because it will be going away. Do we understand this? This is the electric field created by the positive charge. We understand this?
Yes, sir.
Then the negative charge, let me call it as the pink charge. This pink charge will create field in this direction. Which field will win? The green field will win or the blue field will win? Which will be stronger? The green one or the blue or the pink one? Which field would be the stronger one, beta? Green one or the pink one? The green field is created by the positive charge, which is nearer to this point. The pink field is created by the negative charge, which is farther. Which will be the stronger field? The green field will be the stronger field because it is created by charge which is nearer. So the net field will go in the direction of the green field, and that is the field created by the dipole. And you just have to remember the value of this electric field which is created by the dipole, and you can write it like this: 2 times into k. K is your 1 by 4 pi epsilon naught into the dipole moment P into R divided by R square minus L square whole square. This is the magnitude of electric field on the axis of the dipole. Now this is the actual value. So remember, this is the actual value of electric field on the axis of the dipole. This is the actual value. But sometimes what happens is this dipole is actually taken to be very, very small, and this distance is very, very large. So in that case, if your distance r is very, very, very large compared to L, we have a shortcut formula of this electric field. And what is the shortcut formula of this electric field? It becomes 2kp upon r cube. This becomes the shortcut formula of this electric field if the distance is very large. Shortcut formula. But this shortcut formula is only valid when the distance is very large. What are the important points that you must remember about electric field due to a dipole? You must remember these two values. The actual value is 2 times kpr upon r square minus l square, the whole square. Or if you want, you can, instead of k, you can use 1 by 4 pi epsilon naught. I'm just not writing 1 by 4 pi epsilon naught because I just want to save some space. And you must remember this, the shortcut formula. These two formulae must be by hearted by you. The other thing that you must remember is the direction of this electric field. Remember the direction of this electric field. The direction of this electric field. You can see if I have taken the point on the right side, the green charge, which is the positive charge, is stronger. So electric field goes in the direction of away side. If I take the point on the left side also, the field will be coming in the same side. So direction of electric field is along same direction as the dipole moment. So it is always in the same direction of dipole moment. This is a very important point that you must remember. Now, sometimes I have seen a question where they ask you the electric field to a dipole varies on what? So you can write electric field is directly proportional to P and electric field is inversely proportional to R cube. Why I'm writing inversely proportional to R cube? Because in the shortcut formula, you see electric field is 2 kp by R cube. Do we understand this? These are the two things that you must remember about the electric field on the axis of the dipole. I'll give you 2 minutes to read this formula and remember them. This was the electric field due to a dipole on the axis of the dipole. Electric field due to a dipole on the axis of the dipole. Electric field due to a dipole on the axis of the dipole. Then the next thing that we'll have to go through. Have you noted this down, everyone? Yes or no? Boys, have we noted this down?
Yes, sir.
Okay. Then the next thing that you remember, most of the questions that come on dipole are on electric field only. But that does not mean that we should not know the potential. So here comes the next thing, which is the potential due to a dipole. Potential due to a dipole on the dipole axis. So you can write it as case number A and case number B. Case number A is electric field, which is what we have discussed. Case number B is the electric potential, which we are going to write just now. Okay, the screen sharing has gone. Sometimes things happen which are not in your control. So what do? Have patience. Take a deep breath and continue your job. So we move on to the second case. And the second case is the electric potential. Same case as you can see here. I have the electric dipole. The length of the dipole is taken as 2L. Why it is taken as 2L? Because I want the distance is given from the center. I want L and L and I don't want L by 2. Potential of point P. Again, you will have two formulae for potential. One is the actual formula and one is the formula where R is very, very large compared to L. The first formula is like this. Potential at point P is given by Kp upon R square minus L square. Remember, this is the actual formula which is valid everywhere. This is the actual formula. But again, I can have a shortcut formula. If R is very, 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 very large compared to L, looking at the diagram, looking at the formula, can anyone tell me what will be the shortcut formula? It is very easy to see here. What will be the shortcut formula if R is very, very large compared to L? If you understand this, you will have to just remember one. The other one you will already know. Yes, my dear friends. Anyone can tell me what will be the shortcut formula? No one? Okay. So the shortcut formula becomes Kp by R square. L is very less, so we can neglect it. So this is the shortcut formula. So you'll have to remember these two formulae, the actual formula as well as the shortcut formula. I hope you understand them. The actual formula as well as the shortcut formula. And remember this point, potential is directly proportional to the dipole moment and potential is inversely proportional to 1 by R square. These are the things that you must remember about electric field and electric potential created by an electric dipole at any point on the axis of the dipole. I'll give you 2 minutes to note this down. Let me know once you're done. Girls, have you done?
Done, sir.
Girls, have you done?
Yes, sir.
Okay. Now, since we are done with position, which we call the actual position, what should be the next? What should be the next point or the next heading? Tell me, what will be the next heading? We are done for. We are done for axial position on the axis. What should be the next heading? Yes, my dear friend. There were two lines that I showed to you, beta. I think no one is paying attention, it seems. We've done one on the dipole axis. There was a point when I thought that medical students are doing a lot better than JEE ones. Now I feel that, I don't know, that thing is missing. Shown two axes, and if we have done one on the dipole axis, then what should be the next one, beta? It's not rocket science. Can't hear you. Okay, I can't hear you, but I hope you have understood that the next case would be, we will do the same thing on the next axis, and the next axis would be your equatorial axis. So write the next heading, electric field and potential on the equatorial axis. Electric field and potential on the equatorial axis. Equatorial line or equatorial axis, that is case number 2. Equatorial axis. Electric field and electric potential on equatorial axis. And the first case that we will do will be, of course, of electric field. The first case that we will do will be, of course, of electric field. And this is the diagram that you are supposed to draw. I'll show you that diagram. The diagram is here. This is the diagram of the equatorial axis. You can again see the dipole here, and remember, the dipole moment is going from negative charge towards the positive charge, and what you see here is electric field is going in the opposite direction. Do we see this? Yes or no? No or yes? The electric field along the equatorial line is getting cancelled, and electric field is going in the reverse direction. What is the value of this electric field? So you will again have two formulae. The first formula is the actual formula, and the actual formula looks like this: Kp upon r square plus L square raised to the power of 3 by 2, my dear friends. So you have to remember this formula. This is the actual formula. This is the actual formula which is valid everywhere. But again, if R is very, very large compared to L, I can have a shortcut formula. Can anyone tell me what will be the shortcut formula? R is very large, L is very small. Can you tell me what will be the shortcut formula? I would be very happy. No one knows it. Okay, so it is Kp by R cube. This is the shortcut formula. Yes, we neglect L square. Abhiram has got the concept correct. Yes, Abhiram, that is absolutely correct. I was expecting the same from you. This is the shortcut formula. You neglect, nothing else, you neglect. This is the shortcut formula, so you will have to remember both these formulae, the shortcut formula for electric field and the long cut formula for the electric field. This chapter, this topic is all about remembering things. The more you can remember, the better you are. And also you must remember the direction of this electric field is opposite, and I've seen many questions on this, is opposite to the dipole moment. Dipole moment is here, electric field will go there. Then the next thing that you must remember, this electric field is directly proportional to P, and this electric field is inversely proportional to R cube. I will give you 2 minutes to draw the diagram, get your act together, and then we will move ahead. Let me know once you are done, bacha. Do it aram se, there is no haste. Understand the concept, bacha. Remember the diagram. Remember the formula. That is all you can do in this particular case, beta. There is nothing more expected from you. You'll have to remember the formula, and that's it. There is no running away from that fact. Once you're done, bacha, please let me know so that I can move ahead in life. The question from this part would be straightforward. You know it, you take it. You don't know it, you move ahead. It's as simple as this.
Completed, sir.
Well done, sir. Girls, you have completed this? Yes or no? No, yes?
Yes, sir.
Huh? I ask girls, boys. I hear boys voice. So I hope everything is fine. Okay, now we have this diagram, bacha. This is the diagram of electric potential due to a dipole on an equatorial point. And what would you see? It's very, very simple. This is case number B. Case number B, electric potential due to a dipole on an equatorial axis. On an equatorial axis, and you can see both the positive and negative charge are going to create the same potential. So the answer is simply 0. On an equatorial line, the potential created by the potential created by the potential created by the charge, the electric dipole is 0, my dear friends. Please remember it. I'll give you 2 minutes to note it down. Let me know, bacha, once you're done. Done, bacha? Boys and girls?
Done, sir.
Okay, sir. We have a formula for general point. We have a formula for general point. Now, as you can see, this is a general point. This is a general point. The general point, if you remember, this distance was given as r. Do you remember? This distance was given as r, and this is a general point. Now, what is the electric field at a general point? Remember, this angle is theta, that is a general point ka distance makes with the dipole axis. You must remember that your dipole axis is like this. Your dipole axis is like this. Now, if you talk about electric field, the electric field created by this dipole will have two components. One component like this. One component like this. You can call it the radial component because it is along R. You can call it the radial component. Okay, let me color it the same thing so that you can understand. This is a blue component, and I hope everyone is drawing the diagram carefully. We will call it as ER, and the other one is the green component, which we are going to call it as E theta. ER and E theta are the two components. Please draw the diagram very, very carefully. ER, the radial component, the value of ER is given as 2 times Kp cos theta by R cube, blue 1, blue, 2 times Kp cos theta by R cube, and the green one, the E theta one, is Kp sin theta by R cube. So remember these two values, the green component and the blue component. Remember this green component and blue component, and then if you add them, you will get the net value. The net value will be under root of ER square plus E theta square. And if I put the values, but you'll have to remember this, Kp by R cube will come out. Inside the root, you will have 1 plus 3 cos square theta. That is how you must remember it. And then there is an angle you can see here, this pink angle phi. Remember the value of this tan phi. Remember the value of this tan phi. It is half of tan theta. It is half of tan theta. Again, the same thing has happened. I don't know what is happening, but there are things that are not in anyone's control. So what do? You take a deep breath and you chill out. Tan theta is half of, or tan of phi is half of tan theta. I'll give you 2 minutes to note this down. There's still some information that I have to give you, but I will give you that one in the next class. I'll give you time to note this down. Note down all this formulae. We'll come back to this same diagram in the next class. Don't worry about it. Just draw the diagram. You can write it again. Don't worry. I'll come back to this in the next class. So I'll wind off this class here. Take care. Bye-bye. Tell me once you are done, then I can leave. Bye.